Code Soul. Today Jason's going to talk to us about design patterns. Jason has recently started at a new company doing backend engineering, as I understand, using Kotlin. And today's session will be using Kotlin. It is not required for you to know Kotlin, but it is required for you to know some amount of programming. So thank you everyone for coming. Don't forget, you can join our Discord if you want to get more information. And we're all going out for food afterwards. If you would like to join us, we cover the cost. We welcome donations to help offset the cost. But if you don't have income, don't donate. But we'll talk about that more later. And thank you, Jason.
Hi guys, I would like a show of hands of those who've used Java. Okay, I would like a show of hands to those who've used something like, I don't know, what's a nice functional language, or a language with a lot of functional features? JavaScript? Okay, and among those people that have used JavaScript, do you guys know stuff like map, filter, fold? Yeah, if you've heard of them, can you just raise your hand again? Okay, cool. That means I don't need to explain as many things as I thought I would, which is good. But I also made another big mistake of preparing way too much content, which was specifically suggested not to do in the how to give presentation by Beach. So I'm going to give people, I guess, a choice, right? With the design patterns that I'm going to just give a walkthrough of, I could explain the object-oriented code a bit more, or the functional code a bit more. Or, I can just ask per pattern, I want this more functional, or I want this more object-oriented. Who's more interested in the object-oriented stuff? Just raise your hands, please. Okay, who's more interested in the functional stuff? Okay, pretty even split. Okay, I guess I'll go pattern by pattern then. And another question, how many of you guys have actually used design patterns at work or projects or whatever, right? Okay, cool. So mostly unfamiliar. Okay, let's go with that. So yeah, disclaimer, blah, 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 not an expert. I've been coding for almost 3 years at this point, and I've used a little, and I've learned that sometimes they are useful, and in most cases, they are more useful for understanding what the hell is going on, because I found that a lot of library code, like packages, they use a lot of patterns. And like normal day-to-day work, you don't end up, I found myself not really reaching out to those patterns specifically, right? So this is basically my experience so far. So yeah, agenda, introduction, definitions, what kind of problems design patterns solve. I was going to explain abstracts and interfaces and functions as first-class citizens, but I think I would have to explain functions as first-class citizens a bit more instead of abstract and interfaces, because it seems that most people have used Java and some kind of like programming language at a certain point, and they do have similar concepts in other languages as well. So, and then after that, I'm going to briefly, the slides don't actually contain a lot of information. The example code does. So we'll switch over here, and the slides are there to just as filler. And this code here will also be available after the session for you to just peruse over. I'll make a repository on the CodeSoul GitHub. Yeah. And then after that, summary, conclusion, blah, 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 right? So yeah, so how I understand, hold on. Why is my mouse? Okay, never mind. Yeah. So design patterns are basically just, as you see here, reusable solutions to common problems that occur in software engineering. And more specifically, just like writing code itself and just writing logic and just like creating objects or just creating like data structures, and just how these data structures can interact with each other, or how they can be composed together to form much bigger, much complex like objects or data structures. Those kind of problems, those design patterns can help solve, right? So you should see design patterns as tools in a toolbox instead of thinking, oh, I can just slam it into every kind of situation. That's how you end up writing bad code that will haunt you in your dreams. Yeah. Right. So what kind of problems? As I said, just creating objects, composing meaning like how can I put these objects together, and finally how the objects can interact with each other, right? These are the problems that the design patterns solve, right? Abstract interfaces, I'm not gonna go over too deeply. It's something that you guys that are somewhat familiar with, but basically, right, I'm gonna start with the interface first. An interface is just basically a type of, I guess, abstract type that is used as a contract between like classes, right? So an interface is gonna have certain methods, and these methods have to be implemented by the class, right? That implements this interface. An abstract class is a class that cannot be instantiated on its own. It's meant to be subclassed, and it contains both abstract methods, methods without a body that has to be implemented, and concrete methods, so actual methods with actual like logic inside of them. So these are the two tools that are going to be used a lot in object-oriented like design patterns. Any questions so far? No. Okay, cool. And then afterwards, yeah, functions as first-class citizens, right? So functional programming is quite weird if you're just used to object-oriented and procedural programming. The first thing that you have to understand is that functions are first-class citizens, and what this basically means in like an actual programming context is means that you can pass around functions like variables. So if you have a variable called x, you can store a function inside of it, and then you can pass that function out into other functions, and functions can also return other functions, which could be like a crazy concept that is difficult to understand, but I will try to show you with the example code. Another thing that you have to learn about functional programming is that as opposed to object-oriented programming, state is immutable, right? So when an object usually has state, right, a car can have a state called speed, like a property called speed, and that speed object, that speed property in the car can change from like 0 to 50 to 100 back to 50 to 0. And object-oriented programming just exposes methods from the class that allows you to manage the state, which is the, I guess, like the speed of the car. But in functional programming, state is immutable. So that means that whenever a state of a data structure, because I just like objects don't really exist in functional programming, you have to make a copy of the class and then change the data that way. Just make a copy of the class and fill it with new data. So that's like another thing you'll be seeing pretty commonly in functional programming. And another thing is that errors are often handled as values instead of just throwing a exception while just if there is something that the program cannot handle and just stopping the program. Oftentimes in a lot of functional programming, the error is just returned as a value, which means it can be just returned as a string to show like that just something went wrong and you have to handle it instead of just crashing the entire program whenever something goes wrong. So these are like the three, I think, biggest things about functional programming that people get a bit confused about, and which will be used often in the examples that I have. Yeah, but if you were to remember the most important thing is that you can use functions for everything, right? You have to stop thinking in terms of objects, and yeah, you can do really weird things, right? So I have to lay that out first. So yeah, I'm gonna start with behavioral patterns because I think they are the most, simplest and easiest to understand. I will cover, because there are 10 patterns, no wait, how many? No, 4, 7, and 9, right? I will start with these, and then let's look at some code, right? So there are 4 patterns, right? We have the observer pattern, strategy, state, and command. And what the patterns do is a bit more obvious for the behavioral patterns because this suggests like what objects can do, how they interact with each other, or like just how, in case of functional programming, how the functions can interact with each other, right? So if you just look at the words carefully, then you may get a decent hint of what these could mean. So let's look at some code. Yeah, this is so huge. Observer. So FP is the functional programming implementation, and OOP is the object-oriented programming implementation. And this is going to be a demo, right? So let's look at the object-oriented programming first, and then I'm going to run this through a debugger, right? So instead of, let's put a breakpoint right here, right? And I'm just going to also explain the code, so we can, yeah.
Can you make the font a little bigger?
Okay. Hold on. How do I?
IntelliJ IDEA settings, and then editor, font.
Let's make it like 20. Apply. Okay. Is this better?
Yeah.
Okay. So we can see here for the object-oriented stuff, we first create a weather data, right? And then we also register observers, right? We register an observer. This is a forecast display and a current condition display. So this is basically a weather app that shows whenever something changes, the display changes. This is what this class basically does. And then after it registers the observers, it sets the measurements, and let's just actually run through the code, right? So we first start at object instantiation, debug. It's compiling. Yeah, I don't know why Kotlin is compiling so slow. It's not a lot of code, but okay. So we didn't create the object yet, but we first create it, and then, yeah, we first have the object now, here, right? There are no observers at the moment, and the temperature, humidity, pressure is all at 0. Now we're going to register an observer, right? So what is an observer? So this observer here, right, when we look at this weather data, is a list of I observers. This is an interface, right? This means that all observers have to implement this update method, right? There's update method right here. And we are going to add it to the weather data, right? So when we just step into it, we're just going to add it because this is private. You can't access it publicly. We're just going to add it here. Very simple. And we're just going to do it twice. There's forecast display and current condition display. Right? We just step over that. And now we're going to set the measurements. And when we set the measurements, a couple of things are going to happen. We're going to step in. Okay. We're going to set the temperature, set the humidity, set the pressure, and then we're going to notify the observers that a change has happened. So this is essentially what the observer pattern does. You register a couple of observers, right? And then whenever there's a change in state or whatever to an object, you notify what happens to the observers. And depending on how you implemented these observers, right? Because right here, the function is empty, there's nothing in it. It can do a bunch of different things. So let's step into this function here. For each observer, it's just going to update. It's just going to call the update function that we have here, right? It's going to do that. We can see that this forecast display, right? It's just going to update its own last pressure and current pressure, and then it's going to display what the current pressure is and all that kind of stuff, right? So this is what it does, right? This is a very simple pattern, and if you've subscribed to YouTube channels or followed people on Instagram, whenever the YouTube channel or the person just like posts something new, you get a notification. This is something very similar happening, but at a code level. So this is the observer pattern, right? Very simple, yeah. This is the observer pattern. And a functional example of this, right? In functional programming, we do things a little bit differently, right? Here we have the observer interface, and these are implemented here, and they all have the update function, right? So because this is how these classes interact with the weather data class. But here we don't have interfaces. Instead, we have type declarations. And this is a type declaration saying, so this type declaration says that a subscriber is a function that takes in nothing and then returns nothing, right? So any function that like is done in this pattern is going to be treated as a subscriber, right? So like the, so this is basically this, same thing, right? And then, right, the register subscriber, notify subscriber is the same as here. We register observer, remove observer. We don't have the remove method, but like whatever. This is essentially the same thing. We just do it with a function, right? And notify, this is also very similar to here, weather data. Instead of a for loop, we just use a for each, but they essentially do the same thing, right? For observer and observers, we update. And for each observer, we call the function. So if you see here, right, I told you that we can pass around functions like variables. What we have here is a list of functions. And since we named this type declaration as a subscriber, we can put it as a type declaration here. So this is basically a list of functions. And for each function, we will call the function by just with this function calling method, right? Yeah. So this is a subscriber because it takes, yeah. So this is a function of type subscriber. It takes in nothing, and then also returns nothing. It just literally just prints something, right? So yeah. So this is a function, believe it or not, and this is also a function, and these are all functions. We create a list of subscribers, and then we add those, and then we just register them. Then after we register them, we just notify them, right? Subscribers for each subscriber, right? If we just, let me just run through this again. Hold on, let me forecast display. Do I have any other breakpoints? Observer demo, I don't think so. Yeah. Let's just debug. Okay, so we can see that the subscribers is of size 3, and they're all functions, right? You can pass around functions like variables. We go in to the function, and we just, for each, we just call the function, right, 3 times. What this does is just call, like, subscriber 1 dot call the function, subscriber 2 call the function, blah blah blah. It does it like n times. Very simple, very easy, I think, right? Does anyone have any questions so far? Okay, no, cool.
Real quick, can you explain again other cases where the observer pattern might be useful?
Another case,
Maybe a certain database use case that we talked about earlier?
Oh yeah, would that be useful there?
Well, you're doing an event in response, or you're doing an action in response to an event, right?
I'm not sure if I want to couple it like that.
Never mind.
Yeah. But yeah, this is, I think, just useful in cases where you want to add like side effects to whenever something happens in a way that really doesn't interfere with what this class is supposed to do. This class really is only supposed to track weather data, temperature, humidity, and pressure. But if you want to give it a side effect in a more, I guess, like responsible or like makes sense kind of way, yeah, you can use the observer pattern to do that, right? And this weather data, it also doesn't specifically know how these observers are behaving. It only knows that these observers all have the updates method, and they can just be notified when something happens, right? So this is the observer pattern. Cool. This is the observer pattern. Afterwards, we have the strategy pattern, right? I think this could be slightly more useful. So a strategy pattern, right, is used to define a family of algorithms and encapsulate each one and make them interchangeable, right? So we have this duck abstract class here, right? Normally, like when we like implement like something with a behavior, we do just put the logic right here. Put the logic right here, and then if you want to change how this works, right, we would class goose some other duck, right? Let's say just quack behavior. Let me just fly behavior. Let me just fill these in real quick. Blah, blah, blah. If we want to change the behavior of the parent class, we could just inherit it and then just override fun quack and say quack louder, right? This is just like another object-oriented way of doing this, but this kind of like behavior changing by just subclassing and just like overriding stuff, it could, in my opinion, it could get confusing quite fast if you want this behavior to be a bit more interchangeable and customizable, right? So this strategy pattern is a kind of response to that, right? So if you see here, right, you can see that the actual quack and fly, right, it is not actually implemented by the duck class. It takes in a quack behavior and a fly behavior, which each of them like implements their own quack and flies, right? So if you go to quack, they're all interfaces. Right? And what I meant by just a family of algorithms, it's just basically each class, each strategy implementing things in a different sort of way, right? So this is fly. It says flying away. It says I can't fly. Fly with wings. I fly with wings, right? These are different strategies and algorithms, so to speak, right? So if we want to make different like classes that behave in different ways, we can just implement, subclass this duck class, and then put in the specific strategies that we want this class to use. So in this case, the mallard duck would use like a quack and a fly with wings, right? And the rubber duck would squeak and it would not fly, right? So these are two different behaviors, and that we just accomplished it without using any like overriding methods, which can get quite confusing and hard to customize when like the application grows a lot bigger, right? I don't think this, yeah?
Can I add?
Yeah.
So also, this is useful in cases where you want to change the behavior at runtime, right? So let's say that, maybe given some state of your application, right? Maybe it's when it's winter, we want the duck to fly normally, fly south for the winter. And then maybe once it becomes summer, we want them to fly in the opposite direction. So we could have like a fly opposite behavior, right? And with this strategy pattern, you can change the strategy of flying without having to create a whole new duck object.
Yeah. So yeah, so this is called composition, and this is just basically how the objects are composed together to get the behaviors that you want instead of inheritance, which what I explained before as just like becoming a child class of a parent class and just overriding a method, right? Right. So this is most of the time preferred when you write software, right? And this is the object-oriented way of doing it. And the functional way is different, right? We have this door, and all of these are functions. And as I told you before, this is a function that takes nothing and then returns nothing, right? So a door can have a lock, unlock, open, and close strategies. And these are the strategies as defined. So this is a pair. A pair is just basically like a tuple with size 2. It's like a weird data structure that only really, I think, exists in Kotlin. But yeah, this is basically what it is. So it contains 2 functions, right? A function that takes in nothing and returns nothing, so it just prints something. A lock strategy, unlock strategy, blah, blah, blah. There's non-locking, password locking, standard opening, right? And how we use it here is we just create a new like door struct or data class or whatever, and then we just put in the functions that we need, right? And since like open and close and locks and unlocks are functions, when we want to use it, right, we just have to just call it like how we call any other function, right? This is how I guess a strategy pattern is used in a functional way. You just directly pass in the function to the struct or data class or whatever to use, right? So in here, we just passed in classes. In here, we just pass in functions. Right? This is the biggest difference, I think, right? Any questions so far? No? Okay, cool. The state pattern, right? So, who here is like familiar with like games? Who plays games? Games, okay, cool. So the state pattern, right, I think is used often in, I think, games. Because in games, like the state of the player, the state of the world, or like the player world and the state of enemies are constantly changing, and they affect behavior a lot, right? So the state pattern, right, the example I have here is sort of like that, I think. This gumball machine is sort of like, I guess, like a game that you can play. And here, this gumball machine like is like an interactable object, I guess, like in a game, and it can have like multiple different states. It can be sold out. It can have no quarter. A quarter is like a coin. It can have a quarter. It can be sold, and it can be like a winner, right? I will explain what a winner state is, right? But basically, if you look at the class here, right, it doesn't actually implement the behavior itself. It goes to the state first, right? It goes to the gumball machine state, and then it calls the whatever method that it needs to actually call, right? So it doesn't really know or care about the actual implementation details of, you know, how to insert a quarter or eject a quarter, right? It leaves it to the states of the gumball machine. So this is called the state pattern. So depending on the state of the class, the behavior changes, right? And all these things here are, right, this gumball machine state, you can see that here. They all have to implement insert, eject, turn, crank, dispense, blah, blah, blah. So it has quarter states. It has insert quarter, eject quarter, turn crank, blah, blah, blah. And no quarter state, insert quarter, eject quarter, turn crank. Just in case like people maybe not familiar with like a gumball machine is, it's just like, I guess in Korea, like a 뽑기 machine. You just put in like a couple of coins, you just turn something, and like a price comes out, right? This is essentially what it is, right? And you can see here that, yeah, they all implement the method slightly differently, right? So no quarter has quarter. If you just look at these two here, you insert a quarter, right? After a quarter is inserted, the machine state is changed to the machine has quarter state. It turns to this state, this machine, and it has the eject quarters. Like it is implemented differently. It says you have an inserted quarter, and it says quarter returned, right? So after the quarter has been ejected, it gets turned back into a get no quarter state. So within the actual like states implementations, there are ways to just alter the state of the actual class while the behaviors are happening, right? Because without that, it's going to be stuck at one state and only be able to do one thing, which is kind of stupid, right? Has quarter state, machine state. So yeah, so this is how a state pattern works, and to my knowledge, like stuff like state machines and like automata theory, like stuff like that is like a big computer science topic that you may learn in school. So it's kind of like this sort of like hides like a lot of like I think just deep knowledge that you can like look into more on your own, right? So this is the state pattern. Any questions or yeah?
How is state different from strategy?
So the strategy here, right? I would say strategy and state are different in that you can define the behavior, I think, at runtime if you want with the strategy pattern. And for state, it is pretty much fixed. There are only like certain states that this class could be in, and I don't think, unless you do like crazy meta programming to just implement different states at runtime, and I don't think you would want to do that, considering like you're not sure how all the state changes could affect each other, right? So I think the behaviors, I think the main difference is that the behaviors are just kind of just baked in to the class for the state pattern, and for the strategy pattern, it is a bit more malleable, right? I think that would be the main difference. So for this, I think another real-world example is like e-commerce orders, right? This order could have multiple different states. It could be order just could be created. It could be in process. It could be delivered, and it could be confirmed to be delivered. And depending on which state it is, the cancel order process may be different. So that is a actual, I think, example of this like states pattern being used, in the way that it could be used in the real world. And personally, I just think this is just too many objects, right? This is just too many objects, and tracking state changes are just kind of difficult, because as you can see here, we do have a list of like we do have a bunch of states just lined up right here. But if you want to just figure out like how the state changes occur, we have to kind of go in each state and sort of like piece together, oh, if I do this, the state changes that way. But this could be just a problem with like how this class was written. But sometimes it's just simple to use like an if else or like a switch case, which is precisely what functional programming does, right? So this car, right, the example that I used like half an hour ago, I guess, it has a stopped status, a stopped state, and accelerating and decelerating state, right? So when we make a new car, it's going to be obviously be a state of stopped with speed 0. And we can also accelerate and decelerate, right? And instead of just having like a whole bunch of different classes with different behavior, right? We just go through a simple like this is sort of like a switch case or like an if else situation. The when it allows pattern matching, and so it basically enforces that for whatever states the car could be in, either accelerating, decelerating, or stopped, the proper behavior is implemented in the code. So yeah, when it's accelerating, yeah, it can go faster, blah, blah, blah. But according to the states, it can be, when decelerating, right? When accelerating, it can be decelerated, right? And when decelerating, I guess it can either stop or just continue to decelerate. Now that I see that this could also be leading to the stopped state, but I think I forgot to do that when I was just writing this code. So wait, let me just, yeah, no, whatever, it's fine. Or when it's completely stopped, it can just return an error which as a value, which is kind of a thing in functional programming, that car is already stopped, you can't decelerate any further, right? So according to the state, you can have different actions. And this is just, I think in real cases, when I would program something, I would use this either like a pattern matching or like if-else statement, unless the actual behaviors go so absurdly big that I may need to actually use this. But no, I mean stuff like this, right? Because this could all like literally be if-else statements, and I think sometimes that's just fine. It keeps things simple, and you don't have to create a bajillion objects to do everything, right? Any other questions? Any questions? Should I go slower, faster, whatever? It's fine? Okay, cool. Finally, the command pattern. The command pattern is, I think, almost as simple as observer pattern, right? A command is just like telling someone or something to do something. And we can also implement that in code as well, right? I think most people have used a remote control before, right? Right. And so this is what a command pattern can be used as. So we can have a whole bunch of commands saying light on, light off, all that kind of stuff. And depending on like which command is used, we have a different behavior, right? So the light on command needs to be paired with the light on, like actual execution, right? Light on, light off, blah, blah, blah. And if you remember the observer pattern, we like, let's look at the observer again. Where is observer? I can't see it. Okay, here it is. We registered a bunch of like stuff to the class to make the class work. It is in a similar way with the command pattern. So we register a bunch of commands and a command handler, right here. And if we look into this simple remote control, this really doesn't do much, right? It just registers commands and then it just executes them. That's it. It doesn't really know or care about how it's really done. All it has is just a bunch of a hash map of a command and a command handler, right? This command handler just has these two methods that the actual implementation has to implement. So yeah, and all of these classes implement this execute and undo method, right? Let's just go to light on. Pretty simple. This light on, it just takes an I command and it goes light on, light off, right? And whenever the execute is called, it's just going to call light on, right? And it just does that for every single, hold on, commands. Yeah, a bunch of ceiling fan off, ceiling fan on. Yeah, just very simple, blah, 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 right? Stereo off, stereo on. I guess like an immediate like example of where this could be used is like in IoT, right? Whenever like a command happens, you make the command the actual command implementation to do something. Another example of where this could be used is in like a message bus. So whenever like a message gets received of type like I event or I command, the appropriate event or command handler is called from like a internal store, whether it be like an internal hash map or like some other kind of data structure, and then the class or method is just called, right? So yeah, this is the object-oriented way of doing it. The functional way is a lot simpler, right? So this command here is not a interface anymore. It is a function of type that takes in one parameter of type int and then returns a result of type int, right? So when we implement these types, it will take in a number, we'll just add one and then return it, right? and when we execute it, right, we take a value or whatever that we want to do. We also take the command, which is a function, and then we just call the function with the value, right? So yeah, so when I say you can pass around functions like variables, you can just pass them around without it being called, and then you can just call it later in another function, right? So the demo of that. So yeah, you can see that this is a function, so it's like has like a different funky formatting instead of like natural value. So you can just call execute, increment, and value, right? And this is like, I think, I don't think like some patterns work exactly one-to-one well with like, I think functional and object-oriented programming. I think like a lot of the functions evolved as a need because like Java was, I think, a very restrictive language because you only had to do stuff with objects and you can't really just pass around functions or do something weird like that, or just go a bit more loosey-goosey like Python or JavaScript. So sometimes like the examples are just overly simple, and I think that's like one of the reasons why, right? Yeah, pass in a function and you can use the function to do stuff. Pretty simple, right? This is the command pattern. Yeah, let me take a short break and get like something to drink because my mouth is drying up. Yeah.
Questions so far?
With the object-oriented programming example, the last one. Aside from, like, so let's say we omit like low, medium, high, and like volumes, for example. Sure, use that, but wouldn't it be better to use a toggle for like on and off instead of having two because it's less code?
So it depends, right? So if you want to have the same interface where like, there's just a button and the button doesn't track its state and it tracks state internally and you just push the button and whatever the current state is, it just changes, sure. But if you want to say, when I push the on button, it's always on. When I push the off button, it's always off. Even if it's already on or even if it's already off, right? So that's a case where you want to separate. Does that make sense?
Yep. Thank you.
Any other questions with the pattern so far? No? Okay, cool. Yeah, now we're up to structural patterns. This mostly, so behavioral is just mostly about just how the objects behave with each other. Structural is how the objects are just, I think, composed or used together, which is quite, I think, different. Let's start with, let's go bottom up, right? Let's start with a simple example. A facade, yeah, a facade. What's this? Okay, cool. So imagine you're using a whole bunch of like different libraries or like, or a library which is just really complex to use, right? And you want to hide all of that behind like something. You just basically create a function or a class that abstracts away all of the complexity. And this is essentially what the facade pattern is, right? I'm not sure why they gave it like a specific name when I think like facade is just basically a abstraction, but it is what it is. And I haven't seen like good arguments as to why this is quite unique, because essentially like anything that hides complexity but like behind like a layer of like a class or a method is, I think, could be argued as a facade pattern. But since this is like, trying to explain what it is, I had to create a very complex, stupidly complex example, right? In this home theater facade, right? If you want to, watch a movie, typo here. Wait, no. If you want to watch a movie, we have to, turn the popcorn popper on, theater lights to 10, blah, blah, blah. And Yeah, I can see this being used in like an IoT context, but like in most cases when we have to code, I mean, maybe we can come across something like this, but I don't know. It just seems like a very contrived example, and I don't think a facade is actual real pattern, right? So anyway, so we watch a movie, all of these get called. We want to end the movie, all of these get called. Pretty simple. A lot of complexity hidden behind like one function or one class. Very simple, right? Yeah.
So an example is like a remote control, right? You could have, you know, one remote control for volume for your speakers. You could have another remote control for like the cable input to your television. You could have another remote control for how the display is configured. Or you could just have a single remote controller act as a facade for all of those systems. It's the same idea.
So yeah. So do most of you guys do like front end or back end, basically like those kind of stuff, right? No one really does like IoT or embedded. No one really creates like libraries or packages for other people to use, right? I think the stuff here, basically, I think, or I guess also nobody really creates games, right? I think in those contexts, right, where we have to create a lot of objects and these objects have to interact with each other a lot, these patterns would be useful. But like, let's be real, guys. Like when you do backend, like the most complex thing you do, I think, is like just take in like a record from a database, like change it, and then put it back into a database. And like in front end, it just, I don't really do a lot of front end, but it just seems like making like a lot of forms and tables and making a lot of API calls, right? It's not like stupidly complex objects like interacting with each other a lot. So like these cases, it may not happen very often, but I think it is just maybe good to know in case you get like tired of web programming and server programming and decide to do other stuff, right?
I mean, so like for backend, an API gateway
Yeah,
is a type of facade.
yeah,
It's just the infrastructure layers of the code layer.
yeah.
So the concepts are still useful.
It's still useful, and like it's, as I said, it's mostly like just used in like libraries or packages or like weird stuff there. So yeah. Anyway, so this is like an object-oriented example, and a functional example is just going to be super similar. Just a function that calls a whole bunch of different functions, and this here is just like cooking a ramen, right? And you just call this method to call all of these, right? Very simple structural pattern. Yeah. But then now we're gonna go to a decorator pattern. Where the hell? I can't read. Where's the decorator pattern?
Right above this.
Oh, okay, cool. So who here uses Python or have used Python? Okay, cool. Have you guys heard of the decorator? I guess in Python. Yeah, you do the like, the @ sign, and then you put like the decorator on top of a function, and the function gains like additional functionality. Okay, cool. Who used Spring with Java? Okay, cool. That means that you know that all these annotations that you can put on top of like classes or methods, that you can use it to give like additional functionalities to the class or method that you're using. Yeah, I think the decorator pattern is a explanation for that. So what a decorator pattern does, right? It takes an existing class or method, it wraps on top of it, like around it, and then it gives it additional features. It is essentially what it does. And when you just going back to the Python example, right? A decorator, when you just go into the code itself, right? It is a function that takes in another function, and the internal function is the function that the decorator is being placed on top of, right? So so it's a function that takes in another function, and then the function inside calls the other function, and then the whole decorator returns the result of the function that's called internally with what it needs to do, right? a bit difficult to explain, but like, but I think it will be easier when I show you the code, right? So let's say we have to create a coffee object, right? But we want to give it different like features or whatever. So this espresso can become, so like, no, instead of just this like basic coffee here with like just hot water and just coffee, we can add a like chocolate to make it a mocha. We can also add whipped cream, and we can also add like soy milk, mocha, and whipped cream to create like some kind of like other different type of coffee. But instead of just creating like a new class every single time, we can wrap the class, right, in just more classes, right? So let's look at this first. Let's look at beverages, right? So this beverage here, right, it just has the cost and the size and the description, right? And this dark roast, right? It implements the beverage. It subclasses it. And the espresso, like house blend, blah, 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 it just all like implements it, right? So this is like the base like beverage that we're going to add stuff to. The condiments, right? So this is the actual decorator, right? It takes in a beverage, and then according to the condiment, we're going to alter the cost, right? It says not yet implemented. Let's see how it's implemented, right? Because this is of type beverage, right? Despite it being a condiment, right? We can, it's basically treated like a beverage, despite it being a condiment, which is a bit difficult to understand maybe, but yeah, this is essentially what it does. It takes in a beverage, right? And then the cost, it just like, it calls the original like beverage, the cost of the original beverage, and then according to the size, it adds additional costs, right? So this is how we modify the behavior without directly modifying the cost function here, right? Because we could technically, right, have a, you know, list of like condiments here, and we could like, you know, for, you know, condiment, in a condiments, add something, add, you know, additional cost to price. This is also like another way of doing things, but this is, I guess, like a demonstration of how the decorator pattern can do things differently. Personally, I think this pattern is fine when used sparingly, because what this essentially does, right, it creates like a, you know those dolls where you just open it and there's like another doll that's shaped the same way in it, and then you just open it and there's nothing of the same thing? Like what are they called? Like matryoshka? Yeah. Like, wait. Yeah. So this is, I think, basically how the decorator works, if you want to visualize it, right? And when you're like debugging code or trying to fix bugs, I think the more layers of abstractions that you put in, the more difficult it gets. Because if you've tried to like debug a decorator or like a Spring Boot application, the number of like proxies and like different decorators and all these kind of things that the actual like application goes through, it is just so absurdly deep that it's like almost magic to the people using it. So since like a lot of like, I think there's already enough abstraction, so if you can avoid like super deep nested abstractions, then I suggest to you that maybe try a different pattern, right? Or just use something that's like a lot simpler to do, like the for loop that I just showed you, right? So this is a decorator pattern, and yeah, just be careful, right? And for functional programming, yeah, I picked a simple example, So here, this is a function that says chats are cool because they are blah blah blah. So this is going to be decorated. So this journalist is going to decorate this function, right? So it takes in a function that takes in a string that will return a string. So basically this, and it will also return a function that will take in a string and then return a string, right? So to see it actually used, right? So we're adding functionality to the original function by wrapping it in another function, which is basically, I think, how decorators in Python work, right? So it says the news article, right? Right. The news article is just basically going to end up saying that. Let me just run this. Let me just run this real quick. Yeah, dog hating person says this. Chats are cool because they're fluffy. Yeah, it basically just added like this much to this, which is what was originally done by the original function called original speaker, right? So yeah, this is I guess an example of how you can use the decorator pattern in functional programming. Does anybody have any questions? Yeah.
So one quick addition on this pattern. So Jason mentioned that you could accomplish a similar thing to the beverages example just using a loop inside the object, right? But the advantage of the decorator pattern is that the function that you're decorating doesn't need to know about the decorator, right? His beverage cost function can just do its cost and not have to worry about anything else. And then as you add the decorators, it becomes more useful. For example, at the company I work at, we have a data pipelining system. And for some tasks, we want some special monitoring on them. So we just add a decorator to say, monitor this task. And then the task itself doesn't need to know anything about the monitoring system, anything about how to do certain monitoring steps. We just add the decorator and it works. Now, to the point of what Jason's saying about stuff being, how often you'll use these patterns versus finding them in libraries for you, it is very common that a more senior engineer will implement these kinds of patterns for junior engineers to just use and not have to worry about, or to constrain their junior engineers and force them to do things in a certain way to keep things stable and safe. Yeah.
So yeah. So decorators, I think, are useful. Like when what Beach said of logging, if you want to log what happens in a function, I've used logging decorators as well when I was using Python, and a caching decorator for caches. It's kind of useful for that, but I've never really had a case where I had to use it for a class like this. This is just, I think, too much. Literally what I said, I'm a Matryoshka doll, and I don't know. I think what you gain out of having so many layers kind of goes away when you just add way too much stuff. But I don't know. It's useful in certain situations, and where I think it's better to be used a bit sparingly. Right. That is my personal opinion. Right.
May I add?
Yeah. Yeah.
You mentioned earlier that I suppose the majority of us here are web developers.
Yeah.
One way that I use decorators a lot, with Python at least, is for authentication, authorization, and I guess input validation.
Yeah.
Because you might have a user that's not authorized to access certain things.
Yeah.
Or there might be a custom code that allows a user that's not authenticated to
Yeah.
do stuff too. So
Yeah.
I find it useful there.
Yeah. So just adding functionality that the original functional method doesn't really want to know or care about. So useful in those situations. This is a decorator, right? The adapter pattern is what we'll cover next, right? Adapter I found decently useful, although I haven't used it in a way that I have the example for, right? So if we go back to the strategy pattern, right? We have a duck, right? We have a duck with a quack and fly. And all of our code works with this duck, But suddenly, the PM is like, guys, we need a turkey for the Americans because it's Thanksgiving. But it's like, oh no, but all of our code works with duck. What do we do? And then, so we create this turkey with gobble and fly instead of quack and fly. So this is what we do. We create an adapter, right? So we first create this like wild turkey, which implements the turkey, right? But instead of this turkey adapter, right, it implements the duck, right? So the quack and fly with wings, blah, 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 right? And then it's going to take in a turkey. And because it's of type duck, when it quacks and flies, it satisfies the constraints of the duck, but it actually has the behavior of a turkey. So it adapts the turkey to be used like a duck, which is what the adapter does. I guess for like real life cases where I've used this, right, I put it in like the functional example here. So a database, right? Let's say you have a database model. It has the ID and the thing, right? You query it out, you do something, you query it out, turn it into a domain model, then which is like different from a data model, and then you just like do stuff to it, So imagine there's stuff that does not need to be saved in the domain model, right? And then when you want to save to like a database, save to Postgres, right? When we want to adapt it, this is essentially what the adapter does. It changes the interface or like actual class type so that it works with other incompatible types. So this domain model is incompatible with the save to Postgres. So what this, I guess, adapter does, right, air quotes, is when it takes a domain model, it just creates a new database model from this model and just saves it to the database for you so that you don't have to worry or care about the interfaces not matching, right? It adapts the interface. So this is one simple example where it can be used. And a logger, right? Another example is just this logger here. So we can see in this function here where it makes a external API request to something. It has a response and the status code, right? Since it gets past the logger from the parameters here, it just calls the logger and just and logs the response here, right? Let's say we just have a case that we suddenly have to use XML logging instead of using JSON logging, right? But all of our functions are of the JSON logger type. What do? We create an XML logger adapter, right? It takes into XML logger, but it actually returns a JSON logger, right? Right now, it's like a bit of a contrived example because they essentially do the same thing. They take in a string and just does nothing. But yeah, this is a way to adapt a different type to be used. It's a way of adapting one type to be used as a different type. So we look at the demo here, right? This wild turkey, we quack and fly, just forcing it to quack and fly like a duck when it's not actually a duck. Here, this is essentially going to work in a similar way as this. This XML logger, since this is not a JSON logger, we have to wrap it in an adapter, and then pass it into the function to make it work with the current function that we have, right? Instead of having to make another function, right, of XML logger, instead of having to do that, we just pass in an adapter that adapts this XML logger to a JSON logger, right? So yeah, making different types and interfaces work with each other, that's what the adapter pattern does. Yeah. Any questions so far? Nope. Okay, cool. Yeah. Oh, yeah, thanks. just taking a quick break. Yeah, thanks, Peach. So finally, we're going to cover the creational patterns. This is related to creating objects, and I think I saved them for last because I think the factory pattern that I wrote out was just like too amazingly dense and complex that I didn't want to like force it onto you guys from the first go. And the builder pattern, I don't know. The builder pattern, I have thoughts about the builder pattern, right? But like, yeah. So let's start with the builder pattern. So let's say you have an object or like a struct or like whatever that has like 30 different properties and you have to instantiate it. And some of them can be optional, some of them can be not, blah, blah, blah. What do you do? What a sane person would do, right? If you're like working with like a language that allows optional types and like default like parameters, you would just create an object with a constructor that, hold on. Let me just actually just show you, right? You would just do this, right? If you're just creating a complex object and it just has a bunch of values and all that kind of stuff, you know, you just, or set default values, right? Right, this is the sane way of doing things, I think, right? But this is for like standard objects, right? What the builder pattern does, right, is it allows you to create objects step by step, right? We saw from the card here that it takes in a bunch of things like car type, engine, transmission, GPS, blah, blah, blah. And they're all non-nullable and they all have to be filled in. What this car builder does, it allows you set type, set seats, set engine, blah, blah, blah. And when you call the final build method, it will create the object for you, right? Sets type, the type is going to be the type that you set it as, blah, blah, blah. And if there is no like whatever like seat or engine or transmission sets, it will just use the default value, right? So you set, blah, 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 and then finally you build, right? It just does this for you. And imagine that there are like 50 more like properties that you need to fill to make this like pattern like worth it, right? In this case, I don't think it really demonstrates the use of a builder pattern that well, but I have come across cases where I thought the builder pattern was used very well, and that is the case of like query builder. Who uses like a query builder or like an ORM in their work? Yeah. So the problem with using SQL with code is that your compiler or interpreter only really cares if your code is correct. It doesn't really care that your SQL is correct. So if you write SQL queries, you can like do string manipulation to make the queries, and that's just, I tried that. It's a pain in the ass. Just don't try it. So what a bunch of other smart people they came up with, right, was let's make a type-safe way of building queries that just validates that a query is correct when we actually have to run it. And we can see here, we get a query, right? Let me just compare it to the builder pattern here, right? Builder pattern here, the actual demo, yeah. Car builder, set type, set seats. We can see that we can chain the methods inside the class. Then we finally build it. Here it is similar. We can just chain methods like from, where, order by, blah, blah, blah. Do you see the similarities? So yeah, this is the builder pattern where I think is actually useful. Don't use the builder pattern when you can just set optional types and like default values, right? It's just, I think, a waste of time. But in cases where I think the actual thing that you have to build is actually like stupidly complex and just has lots of like user-defined like I think behaviors and complexity, like a query builder, I think it's a perfect time for that. Another way I've seen it used, would the string builder be a builder pattern like in Java?
Yeah.
I mean, with like f strings and like all the other string concatenation stuff, I don't know why you would need it, but it's there. But do you know why?
When you need to progressively build an object.
Yeah.
Maybe you know some of the parts you need to build it now, but you don't know all the parts, but you also don't want to delay the start of building it. So you build some now, you do some other work, you build more later, you do some other work, and then once you have everything assembled, then you say, okay, produce the final object.
Yeah, make sure it is suitably complex before you use the builder pattern. This example here, too simple, right? But I didn't want to create a whole new like query builder by myself because that's just way too much work. Yeah. Functional programming, right? The builder pattern, trying to implement it in a functional way, I had a lot of trouble with because like functional programming is weird. So yeah, here you create, there's a data class struct called house, and a builder takes in a house and it returns a house. So they're building a living room, building a bedroom, building a bathroom. It takes in a house and then adds one to a living room, adds one to a bathroom. Oh wait, no, this is wrong. It adds a bedroom. And since in functional programming, state is immutable, whenever we want to make a state change or like a change to the data, we just create a copy of the data and then we just like change the data that we need to change. So yeah. And what this does, right, it takes a variable number of arguments of type builder, right? And then it folds this, right? What fold does is a bit hard to explain with words, so I can just show you here. It's going to first, for this example here, it's going to, when this is called, right? When this like build function is called, right? It's going to compose the build function with these different functions. It's going to build a living room, right? First by doing this. And then it's going to wrap the result of this in another build bedroom. And it's just going to, matryoshka doll the functions together to finally build the final house, right? But since all of these functions take in a house and return a house, the result is just going to be a house, right? So functional programming a bit weird because you have to just chain functions and just like wrap functions together. So yeah.
So quick note on the creational patterns with functional programming. It doesn't really make sense.
Yeah.
To do,
yeah.
Because a creational pattern is for creating what?
Objects.
Objects. And what do you not have in functional programming?
Objects. Yeah. So yeah, like Kotlin is like a weird mix of functional and object-oriented programming. So I think like, to my knowledge, functional programming, they do have data structures that are similar to objects and classes, but they don't really call it objects and classes. I think they may have like an aggregation of types. I think that's what F# does. They may also have stuff like maps, hash maps, which work similarly to objects. But anyway, it's weird, right? And what's it? And languages that have like functional components in it and doesn't have objects, like I think maybe Golang or Rust, they also do things a bit weird. So all these creational patterns, like, I'm not sure, right? But yeah, if you want to create something little bit by little bit, whatever data structure that you may need in a functional way, this is a way to do it. Yeah. Factory, right? This example is very complicated, so I'll start with the functional one first, right? Even though it does make sense, it doesn't really make sense. So let's say this like game level, right? it consists of a wall, a floor, a mob, which is like an enemy, and a loot, right? And they're all like different, like, just think of them as like hash maps, right? And you have to build it all together. A factory, because this is so amazingly complex, right? I decided to make a factory that makes these game levels for me, depending on what kind of function that I pass in to the factory. So these are all functions, right? They take in a parameter of game level type, and it's going to return a game level type. And you can see that this is just very similar to the builder pattern, right? Here, it just takes in something, it copies it, and then it changes it, right? So what this essentially does, right? The actual like factory, right? It just takes in a game level and it just builds it bit by bit by bit for you in a pre-configured way, right? And this is essentially, I think, what the factory pattern is. There is some kind of factory type, and depending on how it is implemented, the actual consumer of this factory doesn't know or care about how the object is built, but it gets built a certain way that you specify all at once. So let's look at this pizza example, which is unnecessarily complex, right? Let's say you have this pizza, right? And there's a dough, there's a sauce, there's cheese, there's pepperoni, and they're all optional. We don't know how we want to build this. We just want to know that we want to build this according to customer order. And pizza is composed of sauce, cheese, and pepperoni, and they're all different objects, right? What's more complex is that these pizzas, they have a base pizza type, a cheese pizza, anchovy pizza, blah, blah, blah. But they also have like different styles, Chicago style, NY style, so many different pizza types. And the ingredients as well, right? They have base types, anchovy, cheese, pepperoni, but according to the region or style, it could be a mozzarella cheese or like a Reggiano cheese. It could be thin crust dough or thick crust dough, right? For, I think, a factory to be worth using, I think there are two cases, right? The object is just really stupidly unnecessarily complex, then you need to have it made a certain way every single time. Or another like reason that you might want to use it is that you want to quite tightly control how the objects are created within your like code base. A case where I did use it, right, was when I wanted to implement dependency injection on my own for the services that I was going to use it at like API like REST calls. I used the factory pattern then to like just tightly control how the object was created, like what kind of dependencies get inserted into the objects, even though there wasn't like too much complexity in object creation itself, right? Because I just wanted really tight specific control instead of having like people just create objects when they want, how they want, right? Another case is this. I can see this probably being used in, I guess, game programming. I can see that the objects or whatever can get very complex. So here, the actual demo, right? Let's look into the pizza store. Like this is the actual, it takes the actual factory and just does stuff with it. So this pizza store, when you order a pizza, it's going to create the pizza and it's going to prepare, bake, cut, and box it, right? And how this create pizza is actually implemented. Let's go to like a New York pizza store. We're just going to call the pizza factory that is inserted into the NY pizza store. Yeah, too much abstraction. And when we go to simple pizza factory, we can see that it can create a New York style pizza or like a Chicago style pizza, right? And according to the pizza type, it's going to like create a pizza in different ways, right? And these Chicago style anchovy pizzas, blah, 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 they will make the pizzas in a different way because they also take different ingredient factories. So yeah, you can chain a lot of factories and nest them together to make like really complex objects. And yeah, this is how you can use a factory. I personally wouldn't use, I personally wouldn't want to make something so complex in the first place. Like, why does a dough or a sauce or cheese have to be an object? I don't know. But yeah, this was just an example. So yeah, these are all the patterns that I managed to cover today. Does anybody have any questions on the creational patterns? No questions. Okay, cool. Let's go back to, yeah. So yeah, that's it. This is the end of the presentation. These are design patterns. We covered creational, structure, and behavioral stuff, and some examples of design patterns in OOP and functional style. If you want to look up more stuff in much greater detail, refactoring.guru, yeah. This is a good site to use. What is a design pattern? More about the categories, more benefits, blah, blah, blah. There are many more design patterns that I haven't covered that you can look at here. In creational, yeah, there's singleton, prototype. In structural, there's like way more: bridge, composite, flyweight, proxy. Behavioral, chain of responsibility, iterator, blah, blah, blah. Yeah, if you want more detail, go here. They contain code examples in, I think, multiple different ways. First in pseudocode, and then, yeah, code examples in multiple different ways. Right. Just know that these are just additional tools in your toolbox that you could decide to use, right? Just don't think that you have to use these to become like a good developer or anything. You just need more tools in your toolbox. So yeah. So yeah, that's it. That's it for the presentation. Does anybody have any questions?
Yeah.
Yeah.
Why would you choose to talk about pizza so close to dinner time?
Because I am an evil person. I want you to guys to feel hunger. Yeah. Yeah. Yeah, this is it. Done. Yeah.